Welcome to this explainer. Today, we're diving into the absolute biggest bottleneck in robotics right now. We're talking about haptic feedback, specifically how giving machines a real sense of touch is transforming robotic imitation learning from a somewhat clumsy experiment into a highly precise professional discipline. Think about it for a second. How do you actually teach a robot to feel? Imagine trying to tie your shoelaces or maybe pick up a raw egg, but your hands are completely numb. You can clearly see what you're doing, but you have zero physical sensation. Well, that is exactly the problem current AI models face when trying to learn complex physical tasks. They have vision, they have motion, but they are entirely numb. So here's our roadmap for this explainer. We'll look at the massive boom in robot training, the critical missing sense of touch, the haptic hardware stepping up to fix it, the hard data backing this up, and finally, where this is actually being deployed in the real world. Let's start by looking at the sheer scale of the robot training boom. The numbers here are just wild. The humanoid robotics market alone is looking at a staggering 50% compound annual growth rate. We're talking a projected jump from $1.8 billion to an estimated $13.7 billion by 2028. This is heavily fueled by serious venture capital and corporate R&D teams who are all racing to deploy capable humanoids as fast as possible. And zooming out to the broader telerobotics market, it's expected to hit a massive $286.8 billion by 2032. That's a huge leap from around $71 billion in 2023, driven primarily by industrial automation and defense. But there's a massive catch here. Intuitive human control is the bottleneck that's holding this entire fleet back. Which brings us directly to the core problem, the missing sense of touch, and why it creates such a huge bottleneck in imitation learning. You see, in imitation learning, a robot acquires skills by observing a human demonstrator. The operator moves, they look through a VR headset, and they map their visual inputs to the robot's actions. But notice what's missing from that perceptual loop. Force. The perception of force is literally invisible to the system. It captures what you move and what you see, but it captures absolutely nothing about what you feel. And without that gripping force data, the robot simply cannot understand the pressure it's applying. This leads to failed grasps, crushed objects, and really dangerous safety gaps. For the researchers and the data collection specialists out there, you know exactly what this means. Your AI models are getting fundamentally incomplete training data. They struggle to generalize because half of the necessary signal, the actual physical feeling of the task, is just missing. Okay, so how do we bridge this sensory gap? Let's look at the haptic hardware solution. We're talking about incredibly advanced robotics-grade interfaces. Devices like the SenseGlove R1 and Manus setups. These are absolutely not your everyday VR gaming peripherals. They're engineered specifically for professional teleoperation. They create a live, bidirectional feedback loop. When that robotic hand touches something on a real-world assembly line, the human operator feels that exact physical contact right in their own hand. For the engineers, developers, and data folks tuning in, this entire system relies on a super precise 5-layer teleoperation stack. It starts at layer 1, with the human input using the gloves and VR. Layer 2 processes and merges the skeleton data. Layer 3 retargets that data using robust systems like ROS2 and NVIDIA Isaac. Layer 4 is the actual robotic hardware, the dexterous hands. And finally, layer 5 is the feedback, pushing that physical force right back up the stack to the human. Every single layer has to be flawlessly in sync. And the technical specs making this happen are pretty mind-blowing. The SenseGlove R1, for instance, acts as a maximum signal data collection beast. We are talking 20 degrees of freedom with millimeter-level tracking and a blistering 1 kHz update rate control loop with just 10 milliseconds of latency. Using 4 active force actuators and 8 vibrotactile actuators per glove, it instantly renders the robot's applied forces directly onto your fingers. Plus, it has native Python API and ROS2 support, making lab integration incredibly smooth. But let's not just take the hardware's word for it. Let's look at the actual proof in the data and measure the haptic advantage. When we dive into the peer-reviewed research, the value of professional haptics becomes undeniably measurable. Independent labs have confirmed that adding haptic feedback allows human operators to collect training data 6% faster. But it's not just faster, it's vastly better data. This high-fidelity input improves the resulting AI model accuracy by a solid 11%. And crucially, for delicate tasks, operators applied 15% less contact force. That means much more compliant, precise handling of fragile objects without turning them to dust. And the user experience completely backs us up. In a recent study analyzing VR-based robot training frameworks, Over 85% of participants rated the force feedback as highly realistic. What's absolutely wild here is that this held true even for participants with zero prior robotics experience. That is huge because it suddenly opens up the world of robot training to a vastly wider, much more accessible workforce. Now, I want to clarify a critical difference in the hardware landscape right now. Standard VR gloves are designed to give you resistance against purely digital, virtual objects. But true professional robotics haptic gloves, they take physical, real-world robotic pressures, what the robot is actually touching in reality, and feed them directly back into the operator's hands. It is quite literally the difference between playing a video game and remotely operating real, heavy industrial machinery. So let's take a look at where this is moving from the lab into the real world. This data-rich force feedback technology is already being deployed in some incredibly high-stakes environments today. The University of Bonn used this exact tech to help win the $10 million Anna Avatar X Prize for complex social robotic interactions. You'll also see it integrated with UB Tech humanoids, and crucially, the U.S. Department of Energy is utilizing it. Their operators can safely perform nuclear decommissioning and handle hazardous materials from a completely safe remote distance. The use cases are just exploding. Because operators can literally feel what the robot feels, we can conduct remote maintenance in the most extreme, hazardous places on Earth. We can do explosive ordnance disposal without risking human lives. It's totally revolutionizing multi-purpose humanoid robotics training, speeding up industrial automation, and even letting a single expert supervisor seamlessly manage and correct an entire fleet of robots remotely. So if there is one crucial takeaway from this explainer today, it's this. Haptics transform robots from numb, clumsy machines into tactile, intuitive extensions of the human workforce. High-fidelity force feedback is the ultimate bridge. It connects natural human intuition with compliant, professional, robotic manipulation. Simply put, without it, your AI is missing half the picture. And that leaves us with a truly fascinating question to wrap up on. If we can successfully teach a machine to feel exactly what we feel, mapping our incredibly delicate sense of touch across thousands of miles to a hand made of steel and carbon fiber, what previously impossible frontiers will human-machine symbiosis conquer next? Thanks so much for joining me on this explainer. I really hope this sparked some fresh ideas for your own research and robotics deployments.